In this video, we're going to start looking at solving exponential equations. That's what Standard 21 is all about. Now, we're going to start with an application problem to kind of motivate why we may want to be able to solve exponential equations. And this one's going to involve a radioactive substance. And so with radioactive substances, what happens is over time, they decay into other substances. So in this case, it's iodine 123, and iodine 123 atoms, they jettison parts of themselves and become a new element, essentially. But in that jettisoning, you get energy output, and so that's why certain radioactive substances are very dangerous, is because that energy that it emits can be very damaging to anything biological. So in this case, we have this iodine 123, and it says that the half-life is 13 hours. Okay, you're going to hear this term half-life quite a bit, especially in the coming lessons. But half-life just means that it's how long it takes for half the substance to be left. So for iodine 123, it's 13 hours. So that means you have half the iodine 123 you started with 13 hours later. So it says if there's initially 50 grams of this iodine 123, determine how long it takes for the sample to decay to 10 grams. The amount of the substance left after t hours is given by this function. So we already have that function, right? They give that to us. And you can see why it makes sense, right? If you plug a 13 in for t, then you have a 1 in the exponent, which means you're multiplying 50 by a half, which would give you half of the substance left over, right? When you put a 26 in here, that would be 2 half-lives. So you should have a quarter of the substance left over, which is exactly what you get when you take 1/2 to the second power. So you can see why I think we can agree that that's the proper function to use for this. All right, but they're saying, how long does it take to get it down to 10 grams? So we know that we want this to be 10, right? What we're wanting to know is what is t when that happens. So here's our equation that we need to be able to solve. Now what we have here is this exponential equation, and the t is stuck up in that exponent. Now we're going to take two approaches to this, and so this would be over here approach 1. And approach number 1 would be to try to rewrite the exponential in logarithmic form. Now why on earth would I want to do that? The reason I would want to do that is because remember that it looks something like this. If you have b to the y equals x, then that translates to y equals log base b of x. Okay? So in this instance, it's the y that I want to solve for. And if you rewrite it in logarithmic form, then you've got that down out of the exponent and in fact all by itself. Okay, so that would be using the exponential to logarithmic equivalence. So let's try that. But one thing you'll notice is that there's no extra over here with the b, right? Right now I have this 50 over here with the base of 1/2 and the exponent. So I think a logical first step would be to divide both sides by 50. So then I can actually get the logarithm all by itself. But now this has the same form as this. It just looks a little more complicated. So to make that transition to logarithmic form, right, we know that we're going to say that the exponent is equal to the log base 1/2 of 0.2. All right. And I can finish getting t by itself if I multiply both sides by 13. So we have t equals 13 log base 1/2 of 0.2. Okay, so that's an answer, but it's not a very good one for an application problem, right? We'd like to be able to put in our calculator. So in order to do that, remember, we do have the change of base formula available to us, right? So we can say that this is the natural log of 0.2 divided by the natural log of 1/2, right? So right there, we're using this property, log base b of, and how did I write it before just to be consistent? I said the log base b of a is equal to the natural log of a over the natural log of b, right? So that's the property that we're using to get to here. And when I put that into my calculator, I get 30.2 hours. Okay? Now, what I want to do is show you a different approach as well. And the reason I want to show you a different approach is because it tends to be the way I think most people prefer to do these problems because it's kind of nice and easy to remember. And also, there are certain types of problems that you really have to do that way. So it gets a little bit tricky. So while you're more than welcome to use this method of converting from the exponential form to the logarithmic form, I'll just kind of stack the deck in favor of this other one a little bit in telling you that most people prefer approach number 2. You know, why would I even show you approach number 1? Well, it's because it's what you're already familiar with, right? We've done this kind of move of writing the equivalence a lot. All right, let me change colors here so we don't run into the other work that we've done. So here's the other approach. It starts the same as the other one in that I want to get the exponential expression by itself if I can. Okay, but what I'm going to do in the next step is I'm going to take the natural log of both sides. So I'm going to say the natural log of 0.2 is equal to the natural log of 1/2. Oops, that's getting a little messy. I apologize. 1/2 t to the t over 13. So I'm taking the natural log of both sides. Okay. Why would I do that? The reason I would do that is because once you take the natural log of what's on the right here, we can then use the property that we learned that says if you have the log of something raised to a power, that power can come down in front. And so I can bring t over 13 down in front, and that will allow me to get the t untracked from that exponent. So my next step looks like this. Natural log 0.2 equals t over 13 natural log 1/2. All right. And at this point, it's just a matter of getting t all by itself. So if I wanted to get t by itself, I would go ahead and multiply on both sides by 13 on top, natural log of 1/2 on bottom. So I'd multiply that by what I have on the left side. And then I would do the same, of course, on the right side. So then I get some nice canceling here. T is all by itself, and notice that these two things are exactly the same. of course, we also get the 30.2 hours. So this method here tends to be the one that people prefer overall. Take the natural log of both sides and then get that the variable out of the exponent using this property and then go from there. One of the advantages of this is there's no change of base formula needed, because if you take the natural log of both sides, then it's already in that form that can be typed into your calculator. All right, so that started off with a pretty complicated problem. Let's take a step back and do maybe a couple easier ones. But first I want to just talk about guidelines, okay, for solving exponential equations. Okay, so number one, isolate the exponential expression if possible. Number two, take the logarithm of each side, then use the laws of logarithms to get the variable out of the exponent. Or we can rewrite the exponential equation in logarithmic form, right? So those are the two methods we talked about, and then of course solve for the variable. All right, so in this example here in number two, this one, the exponential's already by itself. So if you're going to do the take the natural log of both sides approach, then you're going to say the natural log of 3 to the x equals the natural log of 14. That can come down in front. And then the thing you got to remember here is that, and I didn't really do a good job of stating this on the last page, the natural log of 3 is just a number, right? It looks kind of scary because, you know, you got this L and N there, but the natural log of 3, that entire thing is literally just a number. And so if you have an x times a number, you definitely want to divide by it to get the x by itself. So that gives us x equals the natural log of 14 divided by the natural log of 3. And by the way, I want to do a good job in this section of really distinguishing between exact and approximate, because I will ask you to do give me the exact answer and give me the approximate answer. So exact is this, right? No rounding has been done or anything like that. Approximate is where you've pulled out your calculator, right, and given me some number that's been rounded. All right. Now, just as a side note here, what would the other approach have been? The other approach would have been to rewrite this in logarithmic form. So I would have said x equals the log base 3 of 14. But of course, the change of base formula would allow me to get it in a position to put it in the calculator just like that. So if you, you know, just generally, if I'm just asking for the exact answer, I'm okay with this or I'm okay with this, right? Either one of those is fine. So one of the things that you'll encounter in these problems is that, especially if you're like doing a study guide that I've produced and I show you a solution of mine, it's possible that our solutions will look a little different, but they very well may both be correct. And so that's where, you know, typing it in and getting the approximation is good, because you can double check that, you know, your answer is the same as mine. All right, let's do another one here. So here we have 2 times 5 to the x minus 3 is equal to 14. So I look at this, I might be tempted to immediately take the log of both sides, but let's remember, number one is isolate the exponential expression if possible. So before I go taking the log of both sides, I want to start by getting the exponential by itself. So this will be 5 to the x minus 3 equals 7. And now that the exponential expression's by itself, now it's appropriate for me to take the natural log of both sides. And by the way, let me just actually say this. The common log is totally fine too. Okay, it doesn't matter. So if I use the log, that has a base 10, there's nothing special about the natural log. I don't know, I tend to favor it for some reason. But this is totally correct here. But the big thing is, what do we know? Once we have the log of something to a power, that power gets to come down in front. Now be careful when you do this. This entire thing has to come down in front and multiply by the logarithm. So it's important to put that x minus 3 in parentheses when there's multiple terms up here. So when it comes down, it'll be the log x minus 3 times the log of 5 equals the log of 7. All right, now if you wanted to, you could distribute this through to both of them. That would be totally fine. I kind of like the idea here of immediately getting rid of the log of 5. Right? If I divide by it before I ever distribute anything through, then I just immediately get it off of that side. And so I'm left with x minus 3 equals the log of 7 over the log of 5. And then the only thing left is to add 3. So log of 7 over the log of 5 plus 3. And if I put that in the calculator, it should spit out about 4.21. All right, so in this next video here, we're going to continue to look at solving exponential equations, but here we're going to run into a couple of bumps in the road that we've got to deal with. So in example 4, we look at this and we see we've got variables in the exponents on both sides of the equation. And then we also have this 4 out here that is kind of problematic, and the reason it's problematic is because we know that one of our goals is to get the exponential all by itself. However, that's not possible here, right? So if I divide it by 4 on the left, then that would just put a divided by 4 on the right. So then this one would be by itself, but this one wouldn't. So in this case, we cannot isolate our exponential because we have two different ones. So at this point, we might say, well, is there any way that we can go ahead and just take the natural log of both sides anyway? And we don't really have much else to go on, so let's go ahead and do that. So we'll take the natural log of 4 times 2 to the 3x minus 7 equals the natural log of 3 to the x. All right, now what we have to do at this point is think carefully about what our laws of logarithms say and what they don't say. So the power rule for logarithms that we've been using to solve these problems has been this, right? If you have something that looks like this, you can bring the exponent down in front, and that's what allowed us to untrap the variable from the exponent. Okay, but if you look carefully here, you can apply that without much trouble to the right side, right? You can bring that x down and that looks fine. The capital A is my 3, right? X is my R, works fine. But in this case, it's more tricky because this 4 is not being raised to the 3x minus 7. And here, it doesn't say anything about what to do if you have another number in here. So this property, as it's written, cannot be used on the left side. But here's where we want to remember that this was not the only law of logarithms, right? We also had this one. If I have the product of two things inside the argument of the logarithm, I can turn this into the log base b of a plus the log base b of c. Right? I can turn it into this. And this is going to be important because if I use this property right here, then I can write it as the natural log of 4 plus the natural log of 2 to the 3x minus 7. And now, when I look at the 2 to the 3x minus 7, now there's no other coefficient in front that's not being raised to the 3x minus 7. Now all I have here is this base that you see here. And so now I am allowed to bring it down front. So we have the natural log of 4 plus, now I bring this down, 3x minus 7 times the natural log of 2. And then of course we can do the same thing on the right side here. Okay, so that's where we're at now. At this point, it's kind of a big mess, though, right? And you might struggle to figure out what your next step is. So here's a little trick. If you are ever at a point in your equation and it's getting pretty ugly and you're struggling to figure out what the next step is, over on the side, I want you to make yourself a fake problem. Okay? And your fake problem should look a lot like what you have, except for drop all those natural logs out of it, because they're the things that are really cluttering it up. So let's suppose that your equation was this: 4 plus 3x minus 7. And instead of natural log of 2, let's just say there's a 2 out here. And x times, well, I'm going to put the 3 first, 3 times x. Okay, very similar to what I have, but I took away all the natural logs. And if you ask yourself, okay, what would I do next in this problem? I think that we would all realize, oh yeah, I want to go ahead and distribute that 2 through so that I can untrap the x from parentheses, right? So you would say something like 4 plus 6x minus 14 equals 3x, right? Okay, so if that's your answer for what to do in this simpler looking problem, then that's also your answer for the real problem. So you're going to go ahead and distribute this through to both of those terms. So you'll have the natural log of 4 plus 3x natural log of 2, right? There's no pretty way to combine your 3 and your natural log 2. Well, I guess there is, but it's not worth doing. It might be more confusing than it's worth. So just write it out. So 7 times the natural log of 2 equals this. All right, so one second here. This doesn't look very good, does it? There. All right, so then what do you do next? Okay, you know, and it's quite natural to get stuck again here because, again, this is not the nicest thing to look at. Okay, so let's go back over to our yellow problem. In the yellow one, what would I do next? Well, I'd probably get all the x's on the same side, right? So I might subtract my 6x from both sides. Okay, and once I determine that, I come back over here and say, well, what's the equivalent of my 6x? Ah, it's this one. So yeah, let's get our x's all on the same side. Oops, forgot my 3 there, sorry. All right, so we end up with the natural log of 4 minus 7 natural log of 2 equals x natural log of 3 minus 3x natural log of 2. Now, in the yellow version, we're pretty lucky here because you can just combine like terms, right? So you end up with, negative 3x on the right, 4 minus 14, so negative 10 on the left. Okay, so that doesn't really matter where we're at here. The point is this last step is something that I'm able to do because these numbers are so nice, but I can't quite do it here. So the equivalent of combining like terms when things are just not nice enough to combine easily The equivalent of that is to factor an x out of both terms. Right, and this is the type of thing you had to do back when you were working with um, inverses, right? There were certain inverse problems when you would solve for those. You had to then factor out the variable from more than one term. And as bad as this looks right now, don't forget that this is a number. This is a number. So if you have a number equals x times a number, just like I do here, we know over here we just divide by -3, right? So now we're just going to divide by what's next to the x. So divide by the natural log of 3 minus 3 natural log 2. Okay, and so just to clean up what we've got here, this will be x equals the natural log of 4, oops, natural log of 4 minus 7 times the natural log of 2, natural log of 3 minus 3 natural log of 2. All right, now one of the hard parts of these problems is that depending upon how you decide to go about the problem, your final answer might look quite different. And so what I have here, this is my exact answer, right, as we talked about earlier. So this is a really good one type of problem to make sure you also get the approximate answer. Especially, like I think I've said this before, but you know, if you're comparing your answer to my answer, for example, if we choose to go about things a little bit differently in all this process, we very well may both have the correct answer, but they're just going to look different. So let's type that in our calculator. Now, I want to just take a moment to make sure that we discuss this carefully, because you do have to be careful when you type this kind of stuff in. So everything on top of the fraction has to be in parentheses, and everything on bottom of the fraction has to be in parentheses in order for the order of operations to be interpreted correctly on your calculator. So that becomes difficult when every time you type in a natural log, it's got its own little set of parentheses. So you got to really count up your parentheses pretty carefully. So notice I've got the parentheses around the 4, the parentheses around the 2, so I need another one to close off the top of the fraction. Then I can hit divide, and then I'll put my parentheses, and then natural log of 3 minus 3 natural log of 2. And I close my parentheses again. So you just got to, take an extra second, make sure you got it in accurately. So I get 3.53 when I do that. Okay. And you'll see, on one like this, you really do have to take the log of both sides. Rewriting it in its logarithmic form just wouldn't work. It's too complicated when you've got variables on both sides, each in their own exponent. All right, this would be a good one for you to try before you take a look at my solution. So give it a try first. See how you're doing with these types of problems. All right, so I see that I can't do anything to make it so that both exponentials are isolated. So if I can't do that, then I'm not too bothered by the fact that I have a number on both sides that isn't a part of the base. So the way I would elect to do it is just to go ahead and immediately take the natural log of both sides. Okay, so before using the power rule, we break it up. with the multiplication to logarithm addition rule. And then I can pull these exponents down. So we'll have the natural log of 2 plus x times the natural log of 1.7 equals natural log of 9 plus 2x times the natural log of 3.2. Okay, and so as we've done in the past, we want x's on one side, stuff without x's on the other. So I should do this subtraction, and I can also subtract the natural log of 9 from both sides. So I'll end up with the natural log of 2 minus the natural log of 9. And then we have 2x natural log of 3.2 minus x times the natural log of 1.7. And we've got an x in both terms. I want just a single x, but because it's common to both of those terms, I can pull it out. So x times 2 natural log 3.2 minus the natural log of 1.7. And again, it's just a number equals x times a number, so we divide. So just to clean up here, here's our final exact answer. But let's go ahead and put that in our calculator. When I do, being really careful with my parentheses, I should get negative 0.84. All right, now what I want to do in this example is go back to a topic we've already discussed, which is investing money in an account that earns compound interest. So it says, suppose you invest some amount of money in an account that pays 5% annual interest. How much time does it take for the investment to double when the compounding is quarterly? What if the investment compounds monthly? Okay, so they've asked us to answer this question. Let's take it one at a time here. So quarterly. All right, so we're making an investment. We know that 5% is the annual percentage rate. They don't tell me how much I'm investing. They're just asking how long it takes to double. All right, so remember our general equation here is A of t is equal to A times 1 plus R over K to the KT. So we know R is 0.05, and I guess we know K is 4, right? Because we're talking quarterly. But that's all we know. But because they're talking about the investment doubling, I don't really need to know what A is, right? So if you invest $8 into this account, then doubling it would just mean at the end you have twice what A is. And so this is why, of course, it doesn't matter that we don't know what A is, because they just cancel from both sides. So we're left with this. 2 equals 1 plus 0.05 over 4 to the 4t. All right. So what do we do now? Well, we have this exponential expression. And so let's do what we've been doing. Let's take the log of both sides. So if I take the log of the left and I take the log of the right, we remember that our whole purpose in doing this is so that we can get the variable out of the exponent. And even though this base is really kind of complicated, I can definitely take that base raised, or that base is raised to the 4t. So all of this is raised to the 4t. So I can use my power rule. So I have 4t natural log 1 plus 0.05 over 4. Okay. Now I know that this kind of looks a little bit tough, but this is a number times a variable times another number. Okay. Now, just as an aside here, if you're kind of struggling with this, if over here I said this to you, 2 equals 4x times 8, right? So if that was the problem I gave you, you'd kind of look at it like, what? This is just a strange looking problem. But I think what you would ultimately come to is you'd say, well, okay, 4 times 8, I can simplify that, and you would say, all right, 2 equals 32x, and then you just divide by 32, right? Okay, now that would be the logical way to go about it. Okay, however, there is another way you could do it. So you could not bother to multiply by 4 and 8, and you could just say, you know what, I am going to divide by 4 times 8. That would allow you to cancel your 4. It would allow you to cancel your 8. So x would still be by itself. And then 4 times 8, of course, is 32, which is exactly what you had over here anyway. Right? So you'd still get 1/16 as an answer. So that's all to say, don't let it bother you when there's stuff on both sides of your variable. You can just divide by the product of them. So we end up with the natural log of 2 is equal to 4t natural log 1 plus 0.05 over 4. And I'll just divide by 4 times the natural log of 1 plus 0.05 over 4 on both sides. Those cancel. T is by itself. But of course, this is an application problem. We want to know what the approximation to this is. This might be a good one for us to go ahead and take a look at our calculator on. So I'm going to get out of here, clear this. So typing in what we just discovered, we have the natural log of 2, but again, don't forget about what's in the denominator. So we'll have 12 natural log of 1 plus 0.05 over 4, and then close those parentheses off there. Oh, excuse me, for 12, where did that come from? I was looking at the wrong number. That should be a 4, correct? So 4 natural log of all that. Okay, so we hit enter. 13.95 years, I guess. Okay, so going back here, we can say that t is approximately 13.95 years. Okay, now a good practice to see if you're feeling okay about all this is to do the same thing, but if it compounds monthly, right? If it compounds monthly, what do you get? And I'm not going to do the work for it. I'm just going to give you the answer, but I want you to try to come up with this yourself. You should get something very close to our other answer, 13.89 years. So what is this all about? Well, we're talking about how long does it take for me to double an investment, and we've discussed in the past how compounding more often is a little bit better. So what this is saying is that if you compound your interest monthly instead of quarterly, it's going to take you slightly less time to double your investment than it would if if you did it quarterly. But again, it's a very small difference, right? So increasing your compounding only helps so much.